Okay, this is still section 2.1. We are describing location in a distribution. In the previous video, it was discussed with you about z-scores and how you can convert an individual observation into a z-score, which tells you how many standard deviations that particular piece of data is either above or below the mean. Okay, what we're going to focus on here in this part is we're going to look at transforming data. So you might have a set of data, and maybe the measurements that you collected that data in were, say, in feet, and for some reason you're wanting to convert all of those observations into yards, and so you're needing to perform some operation on all the pieces of data. Okay, whether you're going to add a number to everything, subtract it, multiply, or divide it. That's what we mean when we talk about transforming data. Okay, so when we transform data, what that does is it converts, the original observations from their original units of measurement to another scale. Okay, you're just kind of converting from one unit to another. Now, here's the catch with this. When you do a conversion like this, your transformations are going to affect the shape, the center, and the spread of your distribution. Okay, and it depends on what transformation is happening. Okay, so let's take a look first of all on what effect either adding or subtracting a constant value to all of the pieces of data in your data set, what effect that would have. Okay, so if you could picture, maybe you go around and you ask everybody, I don't know how many siblings they have, okay, and you collect maybe 10 people in your sample, and for some reason you're going to, everyone, you're going to go ahead and let's say that you're going to add 2 more to that. Actually, a better example of this would be, let's say that we have the class's test scores, and then I just add a flat curve of 5 more points onto everybody's score. Okay, that makes a little bit more sense in the context here. Okay, so if I take all your scores, put that on a dot plot, your original scores, but then I choose to add a constant to it, I want you to think about how that's going to cause the dots to shift. Okay, what adding or subtracting a constant to your entire distribution affects is it will change any measures of location, and it will change any measures of center. Okay, now by that we mean measures of location would be quartiles or percentiles. Okay, and by measures of center, we are certainly referring to where the mean and the median would be. Okay, so before the curve, maybe the average score was an 88, but then after I add 5 points to everybody's score, now we're saying, okay, now the average isn't an 88, it's now a 93. Okay, so it affects measures of location and measures of center if you add or subtract. The other piece here is it does not change, though, the shape of the distribution, and it does not change the spread of the distribution. Okay, does not change the shape or the spread. Okay, and by spread, it could be anything from the range, the interquartile range, or the standard deviation. If you think about this, if whatever the low score is and whatever the high score is, if I add 5 points to everybody's score, how much of a span the low is from the high, it's no different. I mean, the low score has bumped up 5 units, but the high score has also bumped up 5 units. So the spread isn't any different, okay? That span isn't any different of how many units it's stretching. Okay, remember, range is a single value. Okay, so here's what we want to memorize. Adding or subtracting a constant to all the pieces in our data set will change your location measures of location and your measures of center, and how it affects that is whatever your measures of center and location were, you're just going to add that constant to that value, okay, or subtract, okay? However, shape and spread stay the same, okay? Now, I want you to look at this example that I created over here off to the side. I don't think this is actually on your notes page, but let's say that you collected some data. You had these values here were in feet, okay? And we want to convert these into yards. So going from feet into yards, we would be, technically, we would divide by 3. Okay, and I just want you to examine the two dot plots and ask yourself, what do you notice that maybe these two dot plots still feel like they have in common, and what are some things that you notice is maybe a little bit different, okay? What we're looking for, has the shape changed when I divided all the values by 3? Has the center shifted? And is the spread different? Okay, so when you're talking about either multiplying or dividing all the pieces in your data set by a number, what that is going to affect, first of all, is it will most definitely affect your measures of center and your measures of location, just like up here when we added or subtracted. Okay, so whatever the previous center was, you would divide that center, that mean or that median, by 3. That's now the new mean and median for the transformed data set, okay? Now, here's the difference, though. The spread now also changes, okay? It either multiplies or divides the spread by, and this is technically, if you were multiplying by a negative number, it would affect it just by like the absolute value of that number. And you can kind of see this in this graph, can't you? Doesn't it feel like this dot plot up here, it was stretched out a little bit more. These dots are more spread out. When I take all these values and divide each one by 3, they're tighter together, okay? If I divide by 3, that makes my spread get smaller. If I multiplied by 3, it would cause this to even span out even more, okay? So it's a little bit more is affected if you're multiplying or dividing. Measures of center, location, and now also measures of spread. However, the one thing that you'll notice remain the same is the fact that the shape didn't change. This still has a little bit of maybe a bimodal or relatively symmetrical look, and so does this one here, even though this one has a tighter spread to it. Okay, so let's look at this example. It says the figure to the right shows the height distribution of one of Mr. Bishop's stats classes along with the summary statistics in the computer output. Okay, so right down here, I'm just going to highlight a couple of things in this computer output. I want to go ahead and start by highlighting just what the mean is. Okay, so what you're looking at here is here we have a nice dot plot. This is the height of his students in his class in inches, and the average height is 67. Okay, the average height is 67. Now it says here, let's suppose that you convert the class's heights from inches to diameters. Okay, I'm sorry, inches into centimeters. Okay, so if we're going to convert from inches to centimeters, here's the calculation that you're going to make. Okay, you are going to have to multiply each observation by 2.54. Okay, now what we're after is we want to figure out how is that going to change the shape of your dot plot if you multiply each of these values by 2.54 and then replot them on a new line. How does that affect, now where's the center? It's probably not at 67 centimeters, okay? And how does that affect the spread, okay? Now the idea here isn't that you actually go through and multiply all these by 2.54. If you know these rules up above, you can basically say what the new center is, what the new spread is. By the way, this right here is the standard deviation. Okay, that's the value in the computer output for the standard deviation. Okay, so if we were to convert all of the class heights from inches to centimeters, first of all, it would have no effect on the shape. Okay, that is the one thing that is not affected. You'll notice in addition, subtraction, multiplication, division, both here, it does not affect the shape, nor does it here. Okay, so the shape would still have the same general trend, okay? But when you multiply, it's going to affect the center and it's going to affect the spread. So now your center, which was 67, is going to get multiplied by 2.54, and I'll show you what that new value would be. The new mean would be the 67 times 2.54. The new mean would be 170.18 centimeters. The new spread, that should also, any of these values here should get multiplied by 2.54. This is my absolute value bars here, 2.54, okay? And if you look at the standard deviation from up above here, the standard deviation was 4.29, so the new spread would roughly be 10.9 centimeters, okay? Everybody see how we're doing that? Okay, so if you're talking about multiplication or you're talking about division, it affects center and spread, addition and subtraction, only the center, and obviously location. All right, so if Mr. Bishop had the students stand on a 6-inch platform and then he had the students measure the distance from the ground, how would the shape, center, and spread of the distribution compare with this original distribution that was given here in inches? Okay, so let's think about how the dot plot would look without actually making it. And this is kind of like my curve example I talked about earlier. It would just take all these dots and it would simply shift all the dots in the dot plot to the right. Okay, that's what would happen if you add 6 inches to everybody's height. Okay, so this is all just getting like bumped over to the right. Okay, so we're talking about addition, we're adding. So if we think about, okay, what's going to get affected? Only any measures of location and any measures of center. The shape should stay the same shape as this dot plot, and whatever the spread is, that should be unchanged as well, which is range, standard deviation, and interquartile range. Okay, so we would say that the shape and the spread will not change, but you should add 6 inches to whatever the center is. So in this example, we would say the new mean would be 67 plus 6. It would be 73 inches if they stood on a 6-inch platform. Okay. All right, now this is really important. It says, now let's suppose that you standardize the distribution. When you see that word standardize, that means you're converting all the values into z-scores. Okay, this was the previous video. Okay, remember when we do this, the way this works is this first value is representing like the individual observation. Okay, so you would take one person's height. Let's just say hypothetically that it was this person here that was 60 inches. Okay, you would subtract from that the mean, which is 67, and then you would divide by the standard deviation, which is this 4.29, and that would give you this person's z-score, how many standard deviations he or she is from the mean. Okay, it says you take the height, subtract the mean, divide by the standard deviation. Okay, so if we were going to convert this, we would want to know then, once you converted all of those, what would be the average z-score and what would be the standard deviation of the z-score dot plot. Now what you see pictured down here is what that dot plot would look like. And I'm going to scroll here. I don't think we can see both of them at the same time, but you can look at it on your paper. You're going to notice that this is the same shape as the original dot plot up here. Okay? But here's what's going to happen. Okay, let me just uncover this a little bit here. All right. Okay, when you standardize the mean, remember what you plug in here, I'm going to take the mean from the original set of data, okay, that mean, I'm going to subtract the mean from it, and then I'm going to divide by the standard deviation. I end up getting 0 divided by 4.29, which is 0. Okay, what that means is anytime you have a set of z-scores, the mean of your z-scores is always going to be 0. Okay, the average of your z-scores will always be 0. And if you were to standardize the standard deviation, now keep in mind here, addition and subtraction is not, standard deviation is not affected by addition and subtraction here. Okay, so when you subtract, let me uncover this here first. Okay. So you're going to take the standard deviation in that set of data, which was the 4.29. The reason I said I'm subtracting nothing is because when we transform this, measures of spread, which is what a standard deviation is, they are not affected by addition or subtraction. So I'm not going to subtract anything from it, but they are affected by division. So I'm going to divide by 4.29, and I end up getting 4.29 divided by 4.29, I end up getting 1. And so when we do this, your standard deviation for a set of z-scores is always 1. Shape stays the same. Okay, so the big takeaway here, and this is super important, okay, and I'm going to go ahead and just highlight this. The mean of z-scores is always 1, and the standard deviation of z-scores, the mean of z-scores is always 0, and the standard deviation of z-scores is always 1, okay? All right, let's look at this example here. It says, during the winter months, the temperatures of the Starnes, Colorado cabin can stay well below freezing, okay? 32 degrees Fahrenheit, which is 0 degrees Celsius for weeks at a time. So to prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She also buys a digital thermometer that records the indoor temperature each night at midnight. Okay. Unfortunately, the thermometer is programmed to measure the temperature in degrees Celsius. Here's a dot plot and numerical summaries of the midnight temperature reading for a 30-day period. Okay, and these readings are in Celsius. So I'm just going to highlight, this is the average Celsius temperature taken at midnight. Now remember, she programmed this for 50 degrees Fahrenheit, okay? But it's Fahrenheit, and our readings here are in Celsius. So we're going to need to do a little bit of a conversion here. It says use the fact that Fahrenheit equals 9/5 times the Celsius temperature plus 32 to help answer the following questions. Okay, first and foremost, it says find the mean temperature in degrees Fahrenheit. Okay, now here's what we need to remember. The mean is influenced by both addition and subtraction and multiplication and division. And that's because the mean is a measure of center. So if I'm going to convert from Celsius to Fahrenheit, and I notice here that I'm adding 32, okay, and I'm also multiplying by 9/5, all of this gets affected by the mean, okay? So down here, I'm going to work this out here. I'm going to take my Fahrenheit formula, and what I'm plugging in for the Celsius temperature is this mean value right here of 8.43. That mean needs to be multiplied by 9/5 and have 32 added to it. That gives me a new mean, and this is in degrees Fahrenheit now, of 47.174 degrees, okay? So it kind of feels like it doesn't seem very accurate because it's supposed to be 50 degrees and the average across 30 days is 47 degrees, okay? Now look at part B. Part B says calculate the standard deviation, which we have this highlighted here, of the temperature readings in Fahrenheit. And then they also want us to interpret this value in context. Okay, so I have the standard deviation in Celsius. I need to use my formula, but I need to think to myself, hold on, standard deviation is a measure of spread. So standard deviation is only going to be influenced by transformations that involve multiplication or division. So when I go to plug in the standard deviation in here, I'm not going to add 32 on the end there, because adding to a measure of spread, that is not something that's going to affect that, okay? So just the multiplication part of the formula gives me 4.086 degrees Fahrenheit. Okay, so once again, notice that standard deviation only influenced by multiplication division. Here is my interpretation. The typical distance of the temperature readings from the mean is about 4 degrees Fahrenheit, okay, which feels like a lot, okay? That's a lot to kind of sway back and forth from the mean there, the typical distance. Okay, and then finally, example C says the 93rd percentile of the temperature readings was 12 degrees Fahrenheit. Okay, I want you to think here about what is a percentile. That's a measure of location, okay? Measures of center and measures of location are affected by addition, subtraction, multiplication, and division. So if I were going to use this formula to convert this 93rd percentile, which is 12 degrees Celsius, I would want to multiply it by 9/5 and add the 32 to it to get 53.6 degrees Fahrenheit, okay? So the new percentile is, the new 93rd percentile rather, is 53.6 degrees Fahrenheit. Okay, on this last page, I just want to talk through really the top of this. The bottom of this is a nice summary that kind of walks through, these are your measures of spread. At the bottom here we have your measures of center. It tells you here pros, cons, formula, and then what's affected, what's not affected by addition or subtraction versus like multiplication, division. Okay, so let's just look at this part at the top. Oh, and one other thing that I will just say here, this is huge. Z-scores, they're not affected at all by any transformation. Your average Z-score is always 0, and your standard deviation is always 1. Okay. All right, so the question here is, what effect on each measure occurs when every observation has 10 added to it? What about every observation multiplied by 3? Okay, so what we're looking at here is we have a data set A. Here is our values. Some of these are measures of spread. Some of these are measures of center. Okay, you don't have the data set to look at. But if you were to add 10 to the entire data set, I want you to think about which of these things would change and how would they change? Well, if you're adding 10, your measures of center should not change at all. So your measures of spread should not change at all. So I'm keeping range, interquartile range, variance, and standard deviation all the same. But my measures of center, the mean and median, those should get bumped up by 10. That would be my new mean and new median. Now, when I multiply by 3, now the mean and median, that would get multiplied by 3, and you're doing this to the original here. So that's 33, and this is 27. My measures of spread now also get multiplied by 3, but there's one caveat here, okay? So I'm multiplying by 3. I'm going to skip variance here for a second. Here's the trick. You got to be really careful about this one. Since the variance is the standard deviation squared, okay, what you're actually doing, and this is the one slight difference here, you do not multiply the variance by 3, okay? The variance gets multiplied by 3 squared, okay? And here's how I want you to think about this, okay? If your standard deviation was 6, then to get the variance, you should square the 6, okay? So this is the only time where you don't multiply by 3, but you multiply by 3 squared if you're changing the